Hi. So welcome everyone to the second lecture in the afternoon. So we will have the privilege to listen to Tjonnie Li from the University of Leuven that will kindly tell us about using time series to identify strongly lensed gravitational waves with deep learning. So I give the floor to Tjon. Many thanks.
Okay, thank you. Just like how Otto started his talk, I just wanted to very much preface that this work was done by Arthur. So he couldn't make it here, both because he had a different conference and he got very sick. So neither way did I manage to take him here. So any difficult questions, ask Arthur. But all kidding aside, I want to take us a little bit back all the way to how Jose kicked off the conference and talk a little bit about how do we actually detect, lensed gravitational waves and then all some of the things that we have to do even before we get to have the joy and try to untangle what it is that we exactly saw. Okay, so the goal, and then here I do have to credit another former student. Especially in strong lensing, our situation is where we get multiple signals from each other, and even saying that, okay, well, does this one look like this one, etc. Okay, so that's really the game when we talk about strong lensing, and we're not even going to talk about all the other fancy stuff that has been presented so far. Simply just asking the question, does this one look like this one, look like that one? Okay, now, when we have to do that, and especially when you look at, in the future, when we do expect, a lot of gravitational waves being detected, is that the detection rate goes up, but the number of pairs goes up 2 arrows. So, for let's say up to 1 million detections in the Einstein telescope, you need to do a lot more pairs and check whether pairs are actually, copies of each other. And so the game is not, is in that sense more difficult compared to, more electromagnetic lensing where you can just point something and you say, okay, well, this clearly looks like, it's lensed. Here, we're a little bit more in the dark. Now, also because, we don't expect many of them to be lensed, it's also inefficient to do, the full analysis for all of the pairs that are available. We have to be a little bit more selective. We have to know, okay, these sort of look alike. Let's investigate these more. And so, just as a small digression, so the way we actually look for gravitational wave signals, Jose talked about this a little bit as well. We use match filtering. And so what I often show is just the process of match filtering is fairly simple. So you got your template, the thing that you're looking for, you're sliding it over with the data. And here in the bottom, you can see the cross correlation. And you can probably all guess where roughly the signal is. Now, this by itself isn't too difficult, right? I can take a template, go through the data, and I get a peek, I look at all the peaks, and I'm done. The problem is we don't know what H, the template, the thing that we're looking for, we don't know a priori what it is. So again, Jose showed something like this. This is a template bank, so mass 1, mass 2, and so for, let's say, all the possible things that we may be able to see. These are binaries that we can see in our gravitational wave detector. We have to somehow filter the data with. So this is actually an old example, but still with the limited sensitivity that we had at that time, we still needed to filter somewhere, close to 250,000 templates, just to cover the parameter space. But reality, even then, isn't that simple. Okay, so things get even more messy. And in particular, it gets messy when, suppose you have a lens signal and you say, okay, well, the template came from here, the thing that I think it's there, why don't I just look for everything else that is just there? Okay, that's a very, that's a very sensible thing to do. Reality really isn't that simple. And so to highlight this, the complexity, I want to take a small detour and show you what I think are fairly remarkable results from what we call a subthreshold search. And so this is the ideal scenario where you got all these gravitational wave signals that you've identified already, and the only thing you have to do is say, okay, do they look similar to each other? But there's also a portion of these signals that are demagnified with respect to the ones that you do see that may be hidden in the data and that you want to go and find as well. And so just to kind of highlight some of the messiness, I want to show you some of the results that we've done on a subthreshold search and show you, some of the complicatedness. Now, on the left-hand side here, you can see what we in our field call pipeline. Don't worry too much about it. It's just a series of steps, things that we do to do our analysis. In this case, when we search for subthreshold, we have the one signal that we want to follow up. And then we do simulations, of weaker versions, stronger versions, and we put them in various different stretches of the data. And then we see, okay, what templates light up. And we use those set of templates to filter through the data again, just to identify whether there's any subthreshold versions, copies of that event in our data. Now, there are many ways in which you can do it. So the first one I started off with saying, maybe the simplest and the most, easy thing to do is just, okay, this yellow dot, that was the template that we found the signal with. Let's just use that one, and we filter through the whole data again. Of course, there's many other choices you can do. Another choice, you can say, okay, I can take the full Bayesian parameter estimation results, and that gives me a nice contour here of 2 sigma, 1 sigma credible interval, and I'm going to take all the templates inside there. That's another way I can do it. I can also do, okay, well, do this whole injection thing where, I inject, I simulate, weaker copies of this signal, and then I run the searches again, the template banks, etc., and then I see all the templates that light up. And then finally, a complete random set of templates. Okay, the most radical thing you can consider doing. So if I want to compare something like this with something that, if I just randomly take the same number of templates, completely random. Of course, you expect them to be the majority to be here because that's simply where most of your templates are. Question? No, it kind of depends on how well we want to cover certain parts of parameter space and whether we believe, there's interesting signals there. And so the coverage is purely a function of what we want rather than anything physical or, And as Jose did mention, it does depend on, the length of the signal, how well you have to space them, but otherwise it's also just physical interest. Bon. I want to ask a question. Out of these 4, which one do we think works best? So show of hands if you think that I just take the exact point that I found, and this is my best way to find all the other copies in the data. Show of hands. Not a trick question. Okay, good, thank you, I appreciate that. Show of hands who thinks, okay, we take the parameter estimation, this is what I think the system is physically. That's already more, good. Some complicated simulation structure where I, simulate multiple copies of things and I put them in the data. And then I filter through that again, different size, only one. And who thinks the complete random thing? Again, it's not a trick question. Okay, good. Somehow people are very, trusting of this completely random thing. Okay, so now this is, so only focus on the top part. And on the y-axis, the x-axis is not too important. It's just given a certain false alarm rate. On the y-axis is the distance with which we can see, potential sources. And in the top, you can see this targeted bank where we do the simulations. And then subsequently, you see the full template bank. So using every single thing. So don't even do further selection. use the full template bank, and then the random bank, and then the parameter estimation bank, and then the single template bank. Okay, so finding these copies and even identifying these copies is really not a trivial thing. It depends on so many things, on the exact noise that was in there that introduces additional complexity into your signal, how much of it is noise, how much of it is signal, etc. So the reason why I show you this is because I really wanted to highlight, I'm very appreciative of all the, I think, fantastic work that a lot of you are doing and trying to really suss out how do signals look, if and when they are lensed by very rich, complicated structures. But in reality, if we actually do need to go and try to identify these signatures, things get a little messy. Okay, now there are other ways in which we can do a quick scan, like do things more or less look like each other. Not the final thing. The final thing is a long, very complex integral to just see, okay, how likely is it that two, sources are the same? One thing I can do is I can simply take the parameter estimation results and I just overlay the two and say, okay, to what extent do the parameters coincide with each other? That seems very reasonable to do, right? If we expect strong lensing, we don't expect a big modification to the signal, so the signal itself should look, the parameters of the signal should look more or less the same. The other thing that we can do is be a bit more agnostic and say, okay, well, I've got these time frequency maps, and I'm going to compare them, pixel for pixel, just to see are the two things similar. Okay, so another, challenge: is this a lensed pair or not? Are these two lensed copies of each other, or could they be lensed copies of each other? Show of hands if you think yes, this is a lensed copy of each other. Show of hands if you think no, they're not lensed copies of each other. Very well, okay. This is actually just Hanford and Livingston of the first detection. So actually we use this to even, do the discovery of gravitational waves. So even there, right, it's a challenge. Even if you just look at this image, it's not immediately obvious whether something like this, could be done. Okay. So one of the ways in which we can do it, especially the fast identification, just sifting through the 10 to 12 possible pairs you may have in the next generation, as with the answer to anything related to science nowadays, is deep learning. Okay, we will all soon be replaced by computers that will do every aspect of what we do. Data analysis, even our theory making everything will be done. And so I'm just helping this trend go forward a little bit more by just saying the answer here could be deep learning. And so what I first showed you is this time frequency map of each other. And so some of the early attempts to do this was specifically using these time frequency maps. And so here I can give you another attempt for redemption. There's one lensed pair and one are just two random signals. See people trying very hard. Again, it's not a trick question. It's not they're all lensed or. I have to look up in the paper which one. I think the top one is lensed and the bottom one isn't lensed, but right, they look fairly similar. So, and that's exactly the idea that they did in Goyal et al. Is they take these images and they use some of the deep learning, especially the image processing technologies in deep learning, to train and see, okay, I'm going to feed it lensed copies of each other or not lensed copies of each other, and you just yank through a lot of data and you're just going to see, okay, can we do it that way? And so this is just kind of a flow of what they do. So they do these Q transform, time frequency transforms, and then they train their convolutional neural networks. Not too important. It is important that they also have the ability, and they've tested this, to add in the sky map. So where in the sky did the source come from with gravitational waves? As long as it roughly overlaps, there's a chance that this works. So they put all of this together, and this is actually a result from the search that we did on O3. So here you see the false positive probability for the machine learning side, and here the posterior overlap. So do the posteriors overlap? And all these dots are possible pairs, of candidates that we found in O3, and we all going to put them, on this thing. So here, the lower, the more confident you are. And so two things should already start, being noticeable. This isn't a very nice y equals x line where, okay, the two methods work more or less on equal footing. There's a lot of stuff here which is, that you can potentially filter out. It's okay, this is not, the false positive probability is fairly high. But still, if you look at these three quadrants, there's still a few signals that we need to then go up and follow up. So this is technology that we do have already, and this is actually being deployed. But the thing here, or the thing that we try to improve upon, is that in this frequency time domain, you lose or you hide the phase information. And as with many of you have shown, there's a lot of rich detail in exactly the way the gravitational wave evolution happens. Right? That's where a lot of the information from the source is. And so our question that we try to answer is, can we make a time domain version of this test? So, okay, so we set out to do this. Before I do so, just a few caveats. When we talk about machine learning, the whole game is just putting data through, right? And so we've made a few choices in the way we do our data, and that is explicitly no lens model. Number one, right? We don't want that, let's say, the frequency of occurrence of certain magnifications, certain time delays to be trained upon a lens model, because if you do, you may end up kind of favoring or not favoring depending on what you've put in. It's a choice. If you're very certain that, okay, I just want to target galaxies, etc., you're more than free to do so. In our case, we don't want to tie it to anything. So we just say, okay, no lens model, no lensing probability for the sources like optical depth, etc. Random image types, also in the unlensed pairs, etc. We just try to, do everything as random as possible. You draw a set of magnifications, time delays, which maps into signal-to-noise ratio of the detector and some random time merger. You create some large data set, and then you do it. So one little caveat, we do make sure that these signals are aligned. So we do assume that we have found them, or in another way we know how to more or less stack it. Although later we will put some uncertainties in this, just in case you don't have a perfect control of exactly where in time you're going to be. Because once you start doing things in a time domain, this is a thing of concern. If you do it in frequency domain, you take the Q transform, fast Fourier transform, and you just have images that you can stack on top of each other. But with time domain, there are more things that you need to think about. Okay, so this is the usual, machine learning thing. I genuinely don't know what this means. But the thing that I want to point you to is the innovation that we've put in here is in order to account for the ability to do time series, is that we need complex, complex weights. The whole infrastructure needs to be based on complex numbers, right? So that's really the additional thing that we've added here. So you can see here all of the activation functions, etc., have to be defined on the complex plane. And other than that, we still use a convolutional neural network, etc. This is the full network, etc. All questions related to these, please send them to arthur.offermans@kleuven.be. And then the question is, okay, let's do a series of experiments. You can more or less guess where all of this is going towards. So, with anything machine learning, we show the ROC curve. So this is the false positive rate versus the true positive rate. And then you draw a curve here. So depending on a fixed or a set false positive rate, how much true positive rate do you have? So you want this curve to be as much on the left top corner as possible. That's your best, best performance. Anything lower is worse. The only thing you need to worry about. Here we've divided into the strength of the signals. So you can see the trend is as expected. The louder the signals, the easier it is to identify something. So far, no good. You don't need ChatGPT to understand this. Okay, now we do go on and say, okay, well, what happens if there is a misalignment? Somehow in the identification of the source, we don't perfectly understand the timing information. What if I now add random deviations from this? And so what you see now here is a difference in the true positive rate. So it's basically, if I take a curve like this, is the difference between this curve and one curve and the other. And here the difference is between different, allowed time, error. So if you stay within, say 5-10 milliseconds, things go well within kind of, more or less some error measurements that we have. Once you misidentify things with 20 milliseconds, that's when you start going wrong and your ROC curve starts plummeting, and we start to panic. But still, with relatively limited time delay errors, and for those who know in gravitational waves, like 10 millisecond, like a few millisecond accuracy is something that we can do. So this works, right? It seems to be working. And so let me just continue in some of the other things that we've checked. So we've checked that suppose you don't have the correct waveform model. And this happens. For those who are working on gravitational waves, they know there's a whole zoo of fancy acronyms for different waveform models tuned with higher modes, with eccentricity, with processing spin, non-processing spin, etc. And so we also wanted to make sure that when you go into a time domain model, right, when things do get, very, it does trace the phase. Then, if you put in a different waveform model, do you go wrong as well? So here we've tested it on the base. That's IMR phenom XPHM. Again, fancy acronym. It just means it's a phenomenological model with processing spin and higher modes. I think I got that right. Yeah, good. I stopped caring after phenom D, and then I stopped caring. But they jumped from D to XP, I think. Don't worry, there's not like the whole series there. Again, what you see here is in comparison to SEOB, I don't want to explain these models. There's some other model with the same amount of physics. So there's also higher modes there, there's processing spin there, and you can see actually the neural network works very well, even though there are discrepancies. There's documented discrepancies, or differences, no, I wouldn't say discrepancy, differences between IMR, phenom P, and SEOB and R. Now, where things do go wrong is if you don't really have the correct physics, because this is IMR phenom, this is where I stopped caring. There you don't have precession, you don't have higher modes. So you do need to have a reasonable complete set of physics inside your models, but it doesn't have to be spot on exactly the thing that nature gives you, which is useful, which is nice. Okay, Morse phase, right? So again, if you do something time domain, what happens if you flip it or half flip it, the signal, is it still robust against those? And more or less guess the answer again here. depending on the different Morse phase or the difference in the Morse phase factor, even if it's a half or if it's one, a complete flip, all of this is something that the machine learner actually manages to catch and make sure that we can still identify through whether something is a lens pair or not. Okay, finally, we're getting very close to the end. This is a comparison with like a first implementation of the Goyal et al. Paper that they use a time frequency, and you can see that in red. And then depending on different time mismatches, but that's not too important, then this is the curve, what you do when you get a time domain version. I have to make the caveat, this is a version where they did not use the sky maps. This is only using the Q-transform portion, which, well, the reason why we wanted to make that comparison is because in order to get the sky maps and everything, you actually need to do a different set of analysis on the signal before you can even get the sky maps, right? So we wanted to kind of start both at the same, just having the raw data, and that's what we are allowed to do. So it's actually performing better than just the time frequency or frequency time. And here we do think that this is a manifestation of the fact that we do have the phase information in there, and we have this comparison. Okay, one last thing, we also use a different kind of machine learning algorithm. We go away from the convolutional neural network, using an attention-based neural network. Again, don't ask me what this means, but we do see that this is the first plot that we made using the convolutional neural network. So this is with the different time delays. So here you can see at 20 seconds, 30 milliseconds, things go very wrong. You can see with the attention base that even this time delay aspect or time mismatch can be mitigated to a certain extent. So even here, just finding better algorithms to do the representation of the time series will help us mitigate some of these problems as well. Okay, so this pretty much brings me to more or less the end. I'll leave this up, I won't read this out, but I also want to stress that all of this technology is not just there, it's not just a manifestation of us needing to find the subthreshold or finding pairs with each other. This is also one route in which we can eventually maybe train, do machine learning to at least identify from a large stack of gravitational waves which ones could have some of the substructure that many of you are working on, which ones of them have it, and those are the ones we may possibly need to follow up. And so just also following onto Graham's talk, you wanted to target some of the gravitational waves that could be lensed, some of the infrastructure here where we hope to be able to rapidly say once a signal has come by, hey, Graham, you may want to point your telescope in that direction. This is also useful for that. Okay, with that, thank you very much.